In this segment, we'll continue our discussion of probability spaces. In the last segment, we introduced the concept of a sigma algebra, and we'll begin this segment by looking at how a sigma algebra can be generated from an arbitrary collection of subsets. We'll also talk about an important class of sigma algebras called Borel sigma algebras. Then we'll go back to our coin tossing example, which we used to establish a connection between sets of binary sequences and subsets of the unit interval. And we'll see how the notion of length for an interval can be generalized to obtain a measure of size for non-interval subsets of the unit interval. And this generalized measure is referred to as Lebesgue measure. And we'll finish by proving a simple and very intuitive result on the monotonicity of probability measures. Suppose we have some sample space omega, and let A be any collection of subsets of omega. We say that the sigma algebra generated by A, denoted sigma of A, is the smallest sigma algebra that contains this collection of sets. Now, to see that sigma of A is in fact well defined and non-empty, note that the collection of all subsets of omega is a sigma algebra, and any intersection of sigma algebras is itself a sigma algebra. So we can define sigma of A as the intersection of all sigma algebras that contain the collection A. Now you should verify that any intersection of sigma algebras must itself be a sigma algebra. In other words, that the intersection is closed with respect to complementation and countable unions. And furthermore, that the set omega itself belongs to the intersection. Now let's consider an example of a collection of sets that's an algebra, but not a sigma algebra, but which we'll later see can be used to generate an important sigma algebra. This is the collection B0 of finite disjoint unions of subintervals, left open and right closed, of the unit interval omega. Now let's prove that this is an algebra but not a sigma algebra. So take any element A of the collection B0, where A is a finite disjoint union of subintervals, and you can see right away that the complement of A can itself be expressed as the finite disjoint union of subintervals. Now some of the listed subintervals may well be empty, but the complement of A clearly belongs to the collection B0. Now let's look at closure with respect to finite unions. So consider another element C of the collection B0. So C is itself a finite disjoint union of subintervals. And in this case, the intersection of A and C is given by the expression shown on the slide, which is obtained by taking all pairwise intersections of subintervals in A and subintervals in C, and then taking the union of all these intersections. And you should verify that this is in fact a finite disjoint union of subintervals, and therefore an element of the collection B0. Now to see that B0 is not a sigma algebra, note that the singleton sets X are not in B0, even though we can express any singleton set as the countable intersection of subintervals. So B0 is an algebra, but not a sigma algebra. Now let's think about the sigma algebra that's generated by B0. So let I denote the set of subintervals of omega, and define B as the sigma algebra generated by I. Now note that B is also the sigma algebra generated by B0. I is a subset of B0, so the sigma algebra generated by B0 can't be smaller than that generated by I. And furthermore, B0 is a subset of B, so the sigma algebra generated by B0 can't be larger than B. And so I and B0 generate the same sigma algebra, which we're calling B. Now the elements of B are referred to as the Borel sets of omega. Now you should verify that this contains the singleton sets, since these can be obtained as the countable intersection of intervals. It includes the rationals, which can be obtained as the countable union of singleton sets. It contains the irrationals, which is the complement of the rationals. And it can be shown that it also contains the normal numbers, which we defined in the last segment. Now recall that the normal numbers are elements of omega whose binary expansion has the same frequency of ones and zeros. Now the Borel algebra also includes the set of non-normal numbers, which is an uncountable set. Now to see that this is an uncountable set, note that it includes binary sequences of the type shown on the slide, where every third term is arbitrary, but all other terms are 1. Clearly the set of such sequences belongs to the complement of the normal numbers. And you can see that this set has a one-to-one correspondence with the set of all binary sequences, and is therefore uncountable. Now more generally, for any metric space omega, if we let O denote the collection of all open sets in omega, then the Borel sigma algebra for omega is simply defined as the sigma algebra generated by this collection of open sets. And members of this sigma algebra are called Borel sets or Borel events. And you should verify that every finite or countable subset of omega belongs to this Borel algebra. Now to see this, just note that the finite subsets are closed, and so therefore their complements are open. And every countable subset of omega is just the union of singleton sets, all of which belong to the Borel algebra. Now, if omega is the set of real numbers, the Borel algebra can be generated by the set of all open intervals. This is because every open set in R can be expressed as the union of open intervals. And the same Borel algebra can be generated by the closed intervals, or intervals that are left open, right closed, and so on. Now, if P is a measure on the Borel sigma algebra, then the triple omega, B of omega, and P is referred to as a Borel space. And if P is a probability measure, then the triple is called a Borel probability space. And in this case, P is called a Borel measure. Now let's go back to our coin tossing example. And we saw that the set of binary sequences, leaving aside the ones that are terminating, is equivalent to omega, the unit interval which is left open, right closed. Now for any subinterval I of omega, define lambda of I to be the length of this interval, and let lambda of the empty set be defined to equal 0. This is a measure of the size of the interval that corresponds to its length. Now for any set A that can be expressed as a finite union of disjoint intervals, define lambda of A as the sum of the lengths of the constituent intervals, and this is clearly well defined. Now I'll state without proof a very important and deep result, and this states that there exists a unique extension lambda star of lambda to the Borel algebra B, such that the triple omega B lambda star is a probability space. Now what do we mean by an extension? We mean that for sets that belong to both B0 and B, lambda star and lambda take on the same value. But lambda star has a much larger domain, so it assigns a measure to sets that belong to B, regardless of whether or not they belong to B0. So lambda star extends the notion of length that we can define clearly for intervals to a much larger class of subsets of the open interval. And this measure lambda star is referred to as the Lebesgue measure. Now this is a probability measure when omega is the unit interval, but we can apply the exact same reasoning to the set of real numbers. And so the Lebesgue measure generalizes the notion of length to non-interval subsets of real numbers. So we can assign a measure to subsets of omega that belong to the Borel algebra B, and we can accordingly assign a probability to subsets of binary sequences that correspond to these subsets of omega. Now I'll finish this segment with a very intuitive result, which states the following. Let omega be any non-empty set, let A be an algebra on omega, and let P be a countably additive function from the algebra to the non-negative extended real numbers. Then for any sets A and B in the algebra, such that A is a subset of B, the image of A under P must be less than or equal to the image of B under P. And furthermore, for any countable collection of sets T in the algebra, whose union is also in the algebra, the image of the union must be less than or equal to the sum of the images. Now note that T need not be a disjoint collection of sets, which is why we have an inequality rather than equality. And the proof is quite straightforward. So first note that P of A is less than equal to P of A plus P of B minus A, since these are all non-negative real numbers, and since the two sets in the latter expression are disjoint and P is countably additive, this latter expression is equal to P of B. Now consider any countable collection of sets in the algebra such that their union is also in the algebra. We'll define a new collection of sets B1, B2 and so on, which are disjoint as follows. So let B1 be equal to A1, and for I bigger than or equal to 2, let Bi be Ai minus the union of all preceding sets in the A sequence. Now note that the sets in the B sequence are pairwise disjoint, and furthermore that the union of sets in the B sequence is equal to the union of sets in the A sequence, which we're assuming to be an element of the algebra. Now verify that each of the sets Bi is itself an element of the algebra, and now note that since P is countably additive and the B's are pairwise disjoint, the image of the union of the sets in the Bi sequence is equal to the sum of the images of the individual sets Bi. This just follows from the countable additivity of P and the fact that the Bi sets are all mutually disjoint. And now we use the fact that each Bi is a subset of Ai, and therefore its image is less than or equal to the image of Ai under P to get the result. So we've proved that if A is a subset of B, then P of A is less than or equal to P of B. And furthermore, for any countable collection of sets T in the algebra, whose union is itself in the algebra, the image under P of the union is less than or equal to the sum of the images of the individual sets in T. Now if A were a sigma algebra, then the requirement that the union of the sets in T belongs to A would be redundant, because every countable collection of sets in A would have a union that belongs to A. And for this special case, we obtain the following result, sometimes referred to as Boole's inequality, which says that for a probability space, for any countable collection of sets in the sigma algebra, the probability of their union is less than or equal to the sum of the probabilities of the constituent sets. And I'll stop there for this segment.